We talked about how there are two different tasks about working with streams in Node, the implementing and the consuming parts, which are completely different. We explored the various events and methods available on both readable and writable streams, and we talked about the two different modes of readable streams, paused versus flowing, and how those affect the way we consume the streams. We then implemented a simple echo writable stream and a simple readable stream, which we used to read the English letters A to Z. We saw how to use the readable stream's read method to push data to consumers on demand. We've then seen some examples for duplex and transform streams and saw how easy it is to compose rich functionalities by piping transform streams into each other. The zlib and crypto modules have some very useful transform streams that can be easily used with each other. While single-threaded non-blocking performance is quite good, eventually, one process in one CPU is not going to be enough to handle an increasing workload of an application. No matter how powerful the server you use can be, what a single thread can support is limited. The fact that Node runs in a single thread does not mean that we can't take advantage of multiple processes and, of course, multiple machines as well. Using multiple processes is the only way to scale a Node.js application. Node.js is designed for building distributed applications with many nodes. This is why it's named Node.js. Scalability is baked into the platform, and it's not something you start thinking about later in the lifetime of an application. Workload is the most popular reason we scale our applications, but it's not the only reason. We also scale our applications to increase their availability and tolerance to failure. Before we talk about scaling a Node.js application, though, it's important to understand the different strategies of scalability. There are mainly three things we can do to scale an application.
The easiest thing to do to scale a big application is to clone it multiple times and have each cloned instance handle part of the workload. This doesn't cost a lot in terms of development time, and it's highly effective. This course module will focus on the cloning strategy.
But we can also scale an application by decomposing it based on functionalities and services. This means having multiple different applications with different code bases and sometimes with their own dedicated databases and user interfaces. This strategy is commonly associated with the term microservice, where micro indicates that those services should be as small as possible. But in reality, the size of the service is not what's important, but rather the enforcement of loose coupling and high cohesion between services. The implementation of this strategy is often not easy and could result in long-term unexpected problems, but when done right, the advantages are great. The third scaling strategy is to split the application into multiple instances where each instance is responsible for only a portion of the application's data. This strategy is often named horizontal partitioning or sharding in databases. Data partitioning requires a lookup step before each operation to determine which instance of the application to use. For example, maybe we want to partition our users based on their country or language. We need to do a lookup of that information first. Successfully scaling a big application should eventually implement all three strategies, and Node.js makes it easy to do so. In the next few clips, we'll talk about the built-in tools available in Node.js to implement the cloning strategy. We can easily spin a child process using the child process node modules, and those child processes can easily communicate with each other with a messaging system. The child process module enables us to access operating system functionalities by running any system command inside a child process, control its input stream, and listen in on its output stream. We can control the arguments to pass to the command, and we can do whatever we want with its output. We can, for example, pipe the output of one command to another command, as all inputs and outputs of these commands can be presented to us using node streams. The examples I'll be using in this module are all Linux-based. On Windows, you'll need to switch the commands I use with their Windows alternative. There are 4 different ways we can use to create a child process in Node: spawn, fork, exec, and exec file. We're going to see the differences between those functions and when to use each. The spawn method launches a command in a new process, and we can use it to pass that command any arguments. For example, here's code to spawn a new process that will execute the print working directory command. We simply destructure the spawn function from the child process module and execute it with the command as the first argument. The result of the spawn function is a child process instance, which implements Node.js event emitter API. This means we can register handlers for events on this child object directly. For example, we can do something when the child process ends by registering a handler for the exit event, which gives us the exit code for that child process and any signal, if any, that was used to terminate the child process. This signal variable is null when the child process exits normally. Other events we can register handlers for this child process instance are disconnect, error, message, and close. The disconnect event is triggered when the parent process manually calls the child disconnect method. An error event is triggered if the process could not be spawned or killed. The message event is the most important one. It's triggered when the child process uses the process.send method to send messages. This is how parent-child processes can communicate with each other. We will see examples of this in the upcoming clips. And finally, the close event is emitted when the standard I/O streams of a child process get closed. Every child process gets 3 standard I/O streams, which we can access using stdin, stdout, and stderr. When those streams get closed, the child process that was using them will trigger the close event. This close event is different than the exit event because multiple child processes might share the same standard I/O streams, and a child process exiting does not mean the streams got closed. Since all streams are event emitter, we can listen to different events on those streams attached to every child process. Unlike in a normal process though, in a child process, the standard out, standard error streams are readable streams, while the standard in stream is a writable one, which is the inverse of those types as found in a normal process. The events we can use for those streams are the standard one. Most importantly, on the readable streams, we can listen to the data event, which will have the output of the command or any error encountered while executing the command. These two handlers here will log both cases to the main process standard out and error. When we execute this script, the output of the pwd command gets printed and the child process exits with code 0, which means no error occurred. We can pass the spawn command any argument using the second argument of the spawn function, which is an array of all the arguments to be passed to the command. For example, to execute the find command on the current directory with a -type f argument to list files only, we pass these 3 strings as values to the array here, and this will be equivalent to executing the command find.-typef, which will list all the files in all directories under the current one. If an error occurs in the execution of the command, for example, if we give find an invalid destination here, we get the stderr line to trigger, and the exit event will report an exit code of 1, which signifies that an error has occurred. The error value here depends on the operating system and the type of error. A child process stdin is a writable stream. We can use it to send the command some input. Just like any writable stream, the easiest way to consume it is using the pipe function. We pipe a readable stream into a writable one. Since the top-level process stdin is a readable stream, we can pipe that into a child process stdin stream. Here's an example. The child process here invokes the wc command, which counts lines, words, and characters in Linux. We then pipe the main process stdin, which is a readable stream, into the child process stdin, which is a writable stream. The result of this combination is that we get a standard input mode where we can type something, and when we hit Ctrl D, what we typed will be used as the input of the wc command, and we get 1 line, 2 words, and 12 characters here. We can pipe the standard input-output of multiple processes on each other, just like we can do with Linux commands. For example, we can pipe the standard out of the find command in the first example to the standard in of the wc command in the second example to count all the files in the current directory. All we need to do is define both child processes and pipe the output of the first one to the input of the second one. I added the -l argument to the wc command to only count lines here. Executing this script here will give us a count of all files in all directories under the current one. And so far we have 3 files here in this directory. By default, the spawn method does not create a shell to execute the command we passed into it, making it slightly more efficient than the exec method, which does create a shell. The exec method has one other major difference. It buffers the command's generated output and passes the whole value to a callback function. Here's our previous example implemented with an exec method. Since exec uses a shell to execute the command, we can use the shell syntax directly here, making use of the shell pipe feature. Exec buffers the output and pass it here in the standard out argument to the callback, which is the output we want to print. If there's an error in the command, the error first argument will be set. Exec is a good choice if you need to use the shell syntax and the data returned from the command is not big, because exec will buffer the whole data before it returns it. The spawn function is a much better choice when the data returned from the command is big, because that data will be streamed with the standard I/O objects, and we can actually make the child process inherit the standard I/O objects of its parents if we want to. Here's an example to spawn the same find command, but inherit the process stdin, stdout, and stderr. So when we execute this command, the data event will be triggered on the process stdout, making the script output the result right away. If we want to use the shell syntax and still get advantage of the streaming of the data that the spawn command gives us, we can use the shell option and set it to true. This way, spawn will use a shell, but it will still not buffer the data the way exec does. This is the best of the two worlds. There are a few other options we can use in the last argument here besides shell and stdio. We can, for example, use the cwd option to change the working directory of the script. As an example, here's the same count all files script done with the spawn command using a shell, and with a working directory set to my downloads folder, which will count all the files I have in downloads, and I obviously need to clean that folder. One other option we can use is the env option to specify environment variables that will be visible to the new process. The default for this option is process.env itself, so any command will have access to the current process environment by default. And if we want to override that behavior, we can simply pass an empty object in the env option, and now the command will not have access to the parent process env object anymore. We can use this env option to manually define environment values and access them in a child command like this one. The last option I want to explain here is the detached option, which makes the child process run independently of its parent process, but the exact behavior depends on the OS. On Windows, the detached child process will have its own console window, while on Linux, the detached child process will be made the leader of a new process group and session. If the unref method is called on the detached process, the parent process can exit independently of the child. This can be useful if the child is executing a long-running process, but to keep it running in the background, the child's standard input-output configuration also have to be independent of the parent. This example will run a node script in the background by detaching and also ignoring its parent standard I/O file descriptors, so that the parent can terminate while the child keeps running in the background. When we run this, the parent process will exit, but the timer.js process will continue to run in the background. If you need to execute a file without using a shell, the exec file function is what you need. It behaves exactly like the exec function, but does not use a shell, which makes it a bit more efficient, but behaviors like I/O redirection and file globbing are not supported when using exec file. On Windows also, some files cannot be executed on their own, like .bat or .cmd files. Those files cannot be executed with exec file, and either exec or spawn with shell set to true is required to execute them. All of the child process module functions have synchronous blocking versions that will wait until the spawn process exits. This is potentially useful for simplifying scripting tasks or any startup processing tasks, but they are to be avoided otherwise. The fork function is a variation on the spawn function for spawning node processes. The biggest difference between spawn and fork is that a communication channel is established to the child process when using fork. So we can use the send method on the forked process and the global process object to exchange messages between the parent and forked processes with an interface similar to that of the event emitter module. Here's an example. In the parent module, we fork child.js and listen on the message event, which will be triggered whenever the child uses process.send, which we're doing every second. To pass down messages from the parent to the child, we can execute the send function on the forked object itself, and in the child, we listen to the message event on the global process object. When running this code, the forked child will send an incremented counter value every second, and the parent will just print that. Let's do a more practical example to using the fork function. Let's say we have an HTTP server that handles multiple endpoints. One of these endpoints is computationally expensive and will take a few seconds to complete. I've simulated this with a long for loop here. This program as is has a big problem. When the /compute endpoint is requested, the server will not be able to handle any other requests because the event loop is busy with the long for loop operation. There are a few ways we can solve this problem depending on the nature of the long operation, but one solution that works for all operations is just to move this computational operation into another process using fork. We'll just move this whole function into its own file, call it compute.js. Then instead of doing this operation here, we fork that file and use the messages interface to communicate messages between the server and the forked process. When we get a request, we'll send a message to the forked process to start processing. The forked process can read that message using the message event on the global process object. In there, we'll call the long computation operation, and once done, we can send its result back to the parent process using process.send. In the parent process, we just listen to the message event on the forked process itself, and once we get that, we have a sum ready for us to send to the requesting user over HTTP. We'll need to import fork for this code to work, and this code is of course limited by the number of processes we can fork, but when we execute this code now and request the long computation over HTTP, the main server is not blocked at all and can take further requests, and when the computation is done, it's received normally as before. Node's cluster module, which we will explore next, is based on this idea of child process forking and load balancing the requests among the many forks that we can create on any system. The cluster module can be used to enable load balancing over an environment multiple CPU cores. It's based on the fork function that we've seen in the previous clip, and it basically allows us to fork our main application process as many times as we have CPU cores, and then it will take over and load balance all requests to the main process across all forked processes. The cluster module is Node's helper for us to implement the cloning scalability strategy, but only on one machine. So when you have a big machine with a lot of resources, or when it's easier and cheaper to add more resources to one machine rather than adding new machines, then the cluster module is a great option for a really quick implementation of the cloning strategy. Even small machines usually have multiple cores, and even if you're not worried about the load on your node server, you should enable the cluster module anyway to increase your server availability and fault tolerance. It's a simple step, and when using a process manager like PM2 for example, it becomes as simple as just providing an argument to the launch command. But I'm going to show you how to use the cluster module natively and explain how it works. Here's the structure of what the cluster module does. We create a master process, and that master process forks a number of worker processes and manages them. Each worker process represents an instance of the application that we want to scale. All incoming requests are handled by the master process, and the master process is the one who decides which worker process should handle an incoming request. The master process's job is easy because it actually just uses a round-robin algorithm to pick a worker process. This is enabled by default on all platforms except Windows, and it can be globally modified to let the load balancing be handled by the operating system itself. The round-robin algorithm distributes the load evenly across all available processes on a rotational basis. The first request is forwarded to the first worker process, the second to the next worker process in the list, and so on. And when the end of the list is reached, the algorithm starts again from the beginning. This is one of the simplest and most used load balancing algorithms. However, it's not the only one. More featured algorithms allow assigning priorities, selecting the least loaded server, or the one with the fastest response time. Let's clone and load balance a simple HTTP server using the cluster module. Here's the simple Hello World HTTP example server, slightly modified to simulate some CPU work before responding. To verify that the balancer we're going to create is going to work, I've included the process ID in the HTTP response to identify which instance of the application is actually handling a request. We'll go ahead and run this server and test that it's working. And before we create a cluster to clone this server into multiple workers, let's do a simple benchmark of how many requests this server can handle per second. We can use the Apache Bench tool for that. I have that tool installed already, but you might need to install that on your system. This command will load the server with 200 concurrent connections for 10 seconds, and our single node server was able to handle about 51 requests per second. Of course, the results here will be different on different platforms, and this is a very simplified test of performance, and it's not 100% accurate, but it will clearly show the difference that a cluster would make in a multi-core environment. Now that we have a reference benchmark, let's scale our application with the cloning strategy using the cluster module. We'll create a new file for the master process. I'll name it cluster.js. This is on the same level as our server.js. In cluster.js, we'll need both the cluster module and the OS module. We'll use the OS module to read the number of CPU cores we can work with. The cluster module gives us a handy Boolean flag to determine if this cluster.js file is being loaded as the master process or not. The first time we execute this file, we will be executing the master process, and the isMaster flag will be set to true. In this case, we can instruct the master process to fork our server as many times as we have CPU cores. This is simple. We just read the number of CPUs we have using the OS module, then with a for loop over this number of CPUs, we call the cluster.fork method. This will simply create as many workers as the number of CPUs in the system to take advantage of all the available processing power. When the cluster.fork line is executed from the master process, the current main module, cluster.js, is run again, but this time in worker mode with the isMaster flag set to false. There's actually another flag set to true in this case if you need to use it, which is the isWorker flag. When the application runs as a worker, it can start doing the actual work. This is where we need to define our server, which we can do by requiring the server.js file that we have already. And that's basically it. That's how easy it is to take advantage of all the processing power in a machine. Let's test. We run cluster.js this time, and on this machine I have 8 cores, so it starts 8 processes. It's important to understand that these are completely different Node.js processes. Each worker process here will have its own event loop and memory space. When we hit our server multiple times now, the requests will start to get handled by different worker processes with different process IDs. Note that those workers will not be exactly rotated in sequence because the cluster module performs some optimizations when picking the next worker. But what we see here confirms that the load is being somehow distributed among different worker processes. Now let's try to load test our server again using the same AB command. The cluster I created on this machine was able to handle 181 requests per second in comparison to the 51 requests per second that we got using a single node. The performance of this simple application tripled with just a few lines of code. The communication between the master process and the workers is simple because under the hood, the cluster module is just using the child process fork API, which means we also have communication channels available between the master process and each worker. We can access the list of worker objects using cluster.workers, which is an object that holds a reference to all workers and can be used to read information about these workers. So since we have communication channels between this master process and all workers, to broadcast a message to all of them, we just need a simple loop over all the workers here. We can use the new object.values to get an array of all workers from the workers object. Then for each worker, we can use the send function to send over any primitive or object value. In server.js, to handle a message received from this master process, we register a handler for the message event on the global process object. Let me remove this previous console log line here to simplify the output, and let's test. Every worker will now receive a message from the master process. Note how the workers here are not guaranteed to start in order. Let's make this communication example a little bit more practical. Let's say we want our servers to reply with the number of users we have created in our database. We'll create a mock function that returns the number of users we have in the database and just have it double its value every time it's called. What we want to do here to avoid multiple DB requests is to cache this call for a certain period of time, let's say 10 seconds. But we still don't want our 8 workers to do their own DB requests and end up with 8 DB requests every 10 seconds. We can have the master process do one request and tell all of the 8 workers about the new value for the user count using the communication interface. In the master process mode, we'll create a function, call it updateWorkers, and use the same loop to broadcast the user count value instead of a text message. Then we'll invoke updateWorkers for the first time, and we'll invoke it every 10 seconds using a simple set interval. This way, every 10 seconds, all workers will receive the new value over the process communication channel. In the server code, we want to use this value that we can read here using the message variable. We can simply create a variable global to this module and set it every time we receive a message. And we can now just use this variable anywhere we want. We'll respond with that variable as well. We need to make this into a write instead of end to output both messages. And let's review. The user count variable here is controlled by the message interface. The master process reset the value of this user count variable every 10 seconds by invoking the mockdb call. Testing this now, the first 10 seconds we get 25 from all workers, and we only did a single DB request here. And then after 10 seconds, all workers will start reporting the new user count, and we only did another single DB request. And this was all possible thanks to the communication channels between the master process and all workers. One of the problems in running a single instance of a Node application versus many is that when that instance crashes, it has to be restarted, and there will be downtime between these two actions, even if the process was automated as it should be. This also applies to the case when the server has to be restarted to deploy new code. With one instance, there will be a downtime, and this affects the availability of the system. When we have multiple instances, the availability of the system can be easily increased with just a few extra lines of code. To simulate a random crash in our server process, let's do a process.exit call inside a timer that fires after a random amount of time. When a worker process exits like this, the master can be notified using the exit event on the cluster object. So we can register a handler for that event, and in there we just fork a new worker process when any worker process exits. It's good to add this condition here to make sure that the worker process actually crashed and was not manually disconnected or killed by the master process, which we're not doing here but might eventually need to. For example, the master process might decide that we are using too much resources based on the load patterns it sees, and it will need to kill a few workers in that case. To do so, we can use the .kill or .disconnect method on any worker, and the exited after disconnect flag will be set to true in that case. So with this if statement here, our code will not fork a new worker for that case. If we run this code now, after a random amount of seconds, workers will start to crash, and the master process will immediately fork new workers to increase the availability of the system. We can actually measure the availability using the same AB command and see how many requests the server was not able to handle overall, because some of the unlucky requests will have to face the crash case, and that's hard to avoid. But it looks like only 17 requests failed out of over 1800 in this 10-second interval with 200 concurrent requests. That's over 99% availability. With these few lines of code, we don't have to worry about process crashes anymore. The master guardian will keep an eye on those processes for us. But what about the case when we want to restart all worker processes when, for example, we want to deploy new code? Well, we have multiple instances running. So instead of restarting them together, we can simply restart them one at a time to allow other workers to continue to serve requests while one worker is being restarted. Implementing this with the cluster module is easy. Let me first comment out this random crash code. We're done with that example. Now, in the master process, we don't want to restart this master process once it's up, but we do need a way for us to send this master process a command to instruct it to restart its workers. Now, this is easy on Linux system because we can simply listen to a user signal like sig usr2, for example, which we can trigger by using the kill command on the process ID and passing that signal instead of killing the process. This way, the master process will not be killed, and we have a way to instruct it to start doing something. Sig usr2 is a proper signal to use here because this will be a user command. If you're wondering why not sig user1, it's because Node uses that for its debugger, and we want to avoid any conflicts here. Unfortunately, on Windows, these process signals are not supported, and we would have to find another way to command the master process to do something. There are some alternatives. We can, for example, use standard input or socket input, or we can monitor the existence of a process PID file and watch that for a remove event. But to keep this example simple, we'll just assume this server is running on a Linux platform. Node works very well on Windows, but I think it's a much safer option to host production Node applications on a Linux platform. And this is not just because of Node itself, but many other production tools which are more stable on Linux. This is just my personal opinion, and feel free to completely ignore it. By the way, on recent versions of Windows, you can actually use a Linux subsystem, and it works very well. I've tested it myself, and it was nothing short of impressive. If you're developing a Node application on Windows and you're not using this new feature, look for Bash on Windows and give it a try. So when the master process receives this signal, it's time for it to restart its workers. But we want to do that one worker at a time, which means only restart the second worker when we're done restarting the first one. So to begin this task, we'll get a reference to all current workers using cluster.workers object, and we'll just store the workers in an array. Then let's have a restart worker function that receives the index of the worker to be restarted. This way we can do the restarting here in sequence by having this function call itself when it's ready for the next worker. So to start this sequence, we'll call this function with index 0 to make it pick the first worker. Inside the function, we'll get a reference to the worker to be restarted using the workers array and the received index. And since we will be calling this function recursively to form a sequence, we need a stop condition. When we no longer have a worker to restart, we'll just return. Then we basically want to disconnect this worker. Now, before restarting the next worker, we want to fork a new worker to replace this one that we just disconnected. We can use the exit event on the worker itself to be able to fork a new worker when this one exits. But we have to make sure that this exit was actually triggered after a disconnect call. So we can use the exited after disconnect flag. If this flag is not true, then this exit was caused by something else other than our disconnect call, and we should just return in that case and do nothing. But if it is set to true, then we'll go ahead and fork a new worker to replace the one that we just disconnected. When this new forked worker is ready, we can go ahead and restart the next one. But remember that this fork process is not synchronous, so we can't just restart the next worker after this call. Instead, we can monitor the listening event on this forked worker, which tells us that this new worker is connected and ready. When we get this event, we can safely restart the next worker in sequence. That's all we need for zero downtime restart to work with the cluster module. To test it, first console log the master process ID because we need that to send the sig usr2 signal. Then start the cluster, copy the master process ID, and I'll restart the cluster in a new terminal, and actually before doing so, I'm going to fire the same AB command to see what effect this restart will have on availability. Start this command first, and right away restart the cluster. So this restart happened while the AP command was load testing our system here. The log here shows how all the workers were restarted in sequence, and this restart did not affect our availability at all. We have 0 failed requests here. Process monitors like, for example, PM2, which I personally use in production, make all the tasks we went through so far extremely easy and give a lot more features to monitor the health of a Node.js application. For example, with PM2, to launch a cluster for any app, all you need to use is the -i argument, and to do a zero downtime restart, you just issue this command. And you can scale the application instances up and down with this command. But I find it helpful to first understand what actually will happen under the hood here. Good things always come with a cost. When we load balance a node application, we lose some features that are only suitable for a single process. This problem is kind of similar to what's known in other languages as thread safety, which is about sharing data between threads and, in our case, sharing data between worker processes. So, for example, with the cluster setup, we can no longer cache things in memory because every worker process has its own memory space. So if we cache something in one worker's memory, other workers will not have access to it. If we need to cache things with a cluster setup, we have to use a separate entity and read write to that entity's API from all workers. This entity can be a database server, or if you want to use an in-memory cache, you can use a server like Redis, or you can create a dedicated node process with a read-write API for all other workers to communicate with. Don't look at this as a disadvantage though, because if you remember the scalability strategies, using a separate entity for your application caching needs is part of decomposing your app for scalability. So you should probably do that even if you're running on a single core machine. Other than caching, when we're running on a cluster, stateful communication in general becomes a problem. Since the communication is not guaranteed to be with the same worker, creating a stateful channel on any one worker is not an option. The most common example for this is authenticating users. With a cluster, the request for authentication comes to the load balancer, which gets sent to a worker, assuming that to be worker A in this example. Worker A now recognizes the state of this user. But when the same user makes another request, the load balancer will eventually send them to other workers which do not have them as authenticated. So keeping a reference of an authenticated user session in one instance memory is not going to work anymore. This problem can be solved in many ways. We can simply share the state across the many workers we have by storing these sessions information in a shared database or a Redis node. But applying this strategy requires some code changes, and that sometimes is not an option. If you can't do the code modifications needed to make for a shared storage of sessions here, there is a less invasive but not as efficient strategy. You can use what's known as sticky load balancing. This is much simpler to implement as many load balancers support this strategy out of the box. The idea is simple. When a user authenticates with a worker instance, we keep a record of that relation on the load balancer level. Then, when the same user sends another request, we do a lookup in this record to figure out which server has their session authenticated and keep sending them to that server instead of the normal distributed behavior. This way, the code on the server side does not have to be changed, but we don't really get the benefit of load balancing for authenticated users here. So only use sticky load balancing if you have no other option. The cluster module actually does not support sticky load balancing, but a few other load balancers can be configured to do sticky load balancing by default.
In this module, we talked about how scalability in Node is something that we start thinking about early on in the process, and talked about the reasons to scale an application and the 3 different strategies that can be used to scale any application: cloning, decomposing of services, and partitioning based on data. Then to explore the Node's built-in modules that will help us with the cloning strategy, we first looked at the different ways we can create a child process using the child process module. We learned about the spawn methods and its events and how to pass it arguments. We looked at how to work with its standard I/O objects and pipe them together when spawning multiple commands. We've seen the various options we can use with the spawn function, like using a shell, customizing standard I/O objects, controlling the environment variables, and detaching the process from its parent. Then we talked about the difference between spawn, exec, and exec file, and then saw an example of forking a process to do a long blocking computation without blocking the main process. We've then scaled the simple HTTP server example using the cluster module and saw how a few lines of code tripled the performance of the server. We saw an example of how to broadcast a message from the master process to all forked workers and how to restart failed workers automatically with the cluster module and how to perform zero downtime restarts as well. And finally, we've talked about the problem of stateful communication when working with clusters and load balancers and how to work around that.
Thanks for taking this course. I hope you enjoyed it and it was a good educational experience for you, and now you feel a lot more comfortable with the Node runtime itself. I've written a Medium article about tips and advice for coders. I thought I'd share some of this advice for you here as I think it's very relevant to this course. The key for any new experience to stick in your mind is practice. Go back to the clips that you were not completely comfortable with and challenge yourself with new matching exercises and implement them. And keep doing so until you're comfortable with the topic. Just like young children, code communicates by misbehaving. Change your attitude toward bugs and problems. It's always great to face them because you'll probably learn something new and it's easy to make progress right then and there. Don't just solve the problems though, understand why they happened. Get comfortable reading and debugging foreign code that you're seeing for the first time. Use interactive debugging when you can, but do not underestimate the value of print debugging. In some cases, print debugging is far more effective than interactive debugging. Don't guess when debugging. Learn how to isolate the issue, perform sanity checks, and only after that, formulate a theory about what might be wrong. Your first instinct will always be to guess. Resist it. Get comfortable reading API documentation and learn the standard libraries for JavaScript and Node. Don't memorize how to use things. Just be aware of the existence of the powerful feature and know how to quickly look them up. Read as many good books as you can, and don't actually just read them, but implement with your hands the examples in them and modify those examples if you can. I say good books because unfortunately there are a lot of confusing and not completely accurate educational resources out there, so you need to pick the healthy ones. I plan on writing a course follow-up article on Medium, and I'll share my recommendation for books and other educational resources for both JavaScript and Node. Node has been changing fast. Very soon there might be a new Streams API that's different from the current one. Follow the Node project on GitHub and its official site to stay up to date with the changes in Node and its ecosystem. And don't forget that you can always ask me questions about any of my courses using this Slack account. Come say hi if you don't have any questions, or if you have any kind of feedback about this course, good or bad. Come chat with me and tell me what could I have done to make this course better for you, and what should my next course be about. Thanks again, and I'll see you in the next course.